So so we'll start this course by uh, so so to begin with, we'll consider. In the last class, I told you that the first. So the okay, just a minute. Somebody is again. Is everyone there, or some? There are 7 students. So is
Sir, all of
everyone?
us are here except Digvijay Singh.
No, Digvijay Singh is anyway not in the course, right?
Actually, he
Is he
was
in the
in the
course?
course previously. I don't know now.
Okay, so who is some? Someone is there in the lobby. Just a minute. I don't know who is there. Okay, so let us begin with special theory of relativity. Okay. And I hope that everyone had done a course on special theory of relativity in BSc. Okay, so maybe BSc and even in the MSc also. In first year, you in electrodynamics there is no mention of special theory of relativity, right? You have not been taught the special
No,
theory
sir.
of relativity in
No, sir.
electrodynamics.
No.
Okay, fine. So anyway, but on the introductory knowledge of special theory of relativity is required. It will be helpful. Anyway, I'm going to cover some part of it. Okay. So before discussing special theory of relativity, let us first do some stuff which we know already. Okay. Suppose we have consider classical physics, okay, or Newtonian physics. Okay. So here also there is relativity in Newtonian mechanics also. Okay, but the rule and the set of equations which we used or which are inbuilt into the Newtonian mechanics are quite different than the one in special theory of relativity. Okay, so suppose we have coordinate system. Okay, suppose we have coordinate system. Let us consider this is x, y, and z. Okay. And we are describing. Okay, let us consider a point in space time. Okay. So let us call this point as P. Okay. Obviously, this P will be having coordinates x, 3, x, y, z that I am writing as vector x, and possibly time. Okay. We have a point in space time. Okay. Its coordinates are labeled by vector x. Vector x, I mean x, y, and z. Okay. 3 numbers and time. Okay. And suppose I have another frame. Okay, suppose this frame is k and this frame is say k prime, which is x prime, y prime, and z prime. Okay, and this frame is moving with constant velocity v. Okay, along x-axis. So all the axes are aligned with each other. The axis of frame k and frame k prime, they are aligned. They are parallel with each other. That means y-axis is parallel with y in k prime and so on. Okay, and this k prime frame is moving with velocity v along x-axis. That is along x prime axis also, because x and x prime are aligned. Okay. Now, what is the suppose if if some observer is situated in this frame, okay, how this observer is going to label this point by these coordinates. Okay, suppose according to observer in K prime, suppose the point remains same, the point P is same. Okay, in both the frame, the point P is same. Okay, it is happening independent of your frame. Okay, so suppose the observer in K prime frame labels this point in the following way: X prime and possibly T prime. Okay, so these are the label used by observer in K prime frame, and these are the label used by observer in K prime. Okay, now by using elementary geometry, okay, you can see that since this frame is moving towards right with velocity v relative to this k, okay, this x prime will be what? Okay, this is the velocity, so distance traveled, suppose at time t equal to 0, okay, origin of k frame, origin of k frame, okay, is same as origin of k prime frame. Okay, so O prime is the origin of k prime frame and O is the origin of k frame. Okay, suppose at t equal to 0, they coincides. Okay, and then you start your clock. Okay, then how this x prime will be related to x? So it is simple equation. So the x minus just vt, because vt will be the distance traveled by the origin. Okay, so the coordinate of this point, okay, as seen by observer in k prime, will be x minus vt, and since this velocity is parallel to x-axis, okay, this there will not be any change along y and along z. Okay, so they will remain same, y prime equal to y and z prime equal to z. Now in Newtonian relativity, or you can say Galilean relativity, okay, this it is assumed that the time remains same in all frames. Okay, so these two frames are called inertial frames. Okay, because they are moving with relative velocity, with constant relative velocity. There is no acceleration, uniform velocity. So in such a case, and in other cases also, the time is assumed to be same. Okay, so time is assumed to be universal. Okay, so there is no transformation in time. Okay, so equivalently, this label is ineffective. This time label, as far as this point is concerned in space-time, this label is ineffective. Okay, we don't need this label t. Okay, what we require is just spatial coordinates. Okay, so this is how your co coordinates. This is how your observer in k prime frame will label the point p in space-time. Okay, and this x, y, and z, they are coordinates of point p in with respect to k frame. Okay, so these simple transformations, these are called Galilean transformations. Okay, so this is just mathematics. Okay, so we have two frames. Okay, and we are labeling the coordinate of a point p, same coordinate, first from k frame and then from k prime frame. Okay, now what is the rule? Okay, the Galilean relativity or Newtonian relativity says that all it says that laws of motion in all inertial frames are same. That means any equation of motion, okay, written in k frame will not change its form if you transform according to this transformation to K prime frame. Okay, so you take the free particle, you take the particle subjected to force, okay, and write down the equation of motion. Its form under this transformation remains same. Okay, so for example, if you consider a free particle, okay, so what is the free particle equation of motion? It is d2m, force is 0, so d2x, so I'm just considering the x-axis, y and z will be trivial. Okay, d2x by dt square will be 0. Okay, now suppose if I want to transform in, this is in K frame. Okay, suppose I want to transform in K prime frame. What you need to do, from this you can find the inverse transformations, right? You can find the, if this is the transformation which takes you from this frame to this frame, then obviously a transformation which takes you from K prime to K frame will be x prime plus vt. Okay, y equal to y prime, z equal to z prime. Okay, and t remains same, so you can replace t by t prime. Okay, so you can find the inverse transformation from this, okay, and substitute here, substitute for x. So in K frame it will be m, okay, d2 by dt prime, which is same as t, okay, and x prime plus v t prime. Okay, so obviously this is second derivative in time, this is a constant, this is a linear function in time, so again you will get m d2 x prime by dt prime. Okay, so this transform to 0, this is equal to 0. So in K prime frame also you have same equation. What do I mean by same equation? What I mean is the following: the transformations here are such that there is no, this transformation won't generate any first derivative or any quadratic derivative terms. Then it will be different. Okay, suppose instead of this, suppose if my transformations are such that if I generate, apart from this d2 x prime by dt square, dt prime square, suppose if I generate some alpha times dx prime by dt, where alpha is dimensional, correct, has correct, alpha together with this has correct physical dimension as force. Okay, there is a m here. Okay, so it has correct physical dimension of acceleration. Okay, so these transformation won't generate terms like this, otherwise it is different equation of motion. Okay, the form remains same means it will not generate any more derivative terms, okay, or any other term. It will not even generate the constant here. There is no constant here. Okay, because if there were any constants, okay, we can, there is a way to prefer one frame to another over another. Okay, if there were, if suppose if there is some constant here, okay, instead of 0 here there is some constant here. Okay, there is a way to prefer K prime frame over K frame. If somebody likes this constant, okay, he can choose this frame. Okay, so there is a way to give preference to among the frames. Okay, but that is not allowed. What this rule says is that all frames are essentially same. As far as they are inertial, all frames are essentially same. This is what it says. Okay, so this is there in, so the principle of this called principle of Galilean relativity, this will remain same in special relativity also. Okay, okay, but what is the consequence of this? Okay, why one want to go into the special relativity? Okay, although the equation of motion, ordinary equation of motion like of classical particle, preserve its form under this Galilean transformation. Okay, you can also consider second example. You consider some definite force law and see, suppose the particle is subjected to some force. Sorry, there is no t prime here. Some force, say force equal to mg. Okay, then you transform according to this, and you will see that the form of equation remains same. Okay. So although the equation of motion for this classical particle preserve its form under this Galilean transformation, there is a problem. Okay. Suppose we want to discuss within the classical physics, suppose we want to discuss Maxwell equations. Okay. What are the Maxwell equations? So you have del dot E. So I'm using suppose you consider sourceless Maxwell equation. There are no sources. Okay. So what are the equations? Okay. Del dot E equal to 0. So there is no rho there. Okay. And then there is del dot B equal to 0. These are divergence equations. And del cross B is equal to 1 over mu 0 epsilon 0. So I'm assuming you have done Maxwell equations, you have seen Maxwell equation, and I will just write C here. Okay. Del E by del D. And there is another equation, curl of E equal to minus del B by del D. Okay. So here your C is basically 1 over square root of mu 0 epsilon 0. Okay. So this I have used. Okay. So what is the problem? Okay. The problem is the following. Suppose if I consider, say for example, this equation. Let us consider this equation. If I show that this any one of this equation does not preserve its form under Galilean transformation, then I am done. Then I can say that the Maxwell equation does not preserve their form, okay, with respect to Galilean transformation. Okay, you can choose any equation in this. Okay, this will not give any new information because it's simple. Okay, but let us consider this or this. You can consider this also. Okay, so for simplicity, okay, see if I can transform this equation by assuming some particular form of E and B. Okay, I will keep the functional form arbitrary, but I will choose the electric field and magnetic field in specific directions. Okay, okay. Let me choose your electric field. So in K frame, so these are, all these equations are in K frame. Okay, so let us consider my electric field. I will choose my electric field just for a simplicity. You can do uh, general thing also, right? There is no point in doing this. This is the electric field. It depends on space, okay, x, y, z, and time. Suppose if I choose this electric field in the following way, okay, electric field, I will say that it depends on time, okay, and it depends on x coordinate. It will not depend on y coordinate. It may happen, right? Y and z coordinate. It will not depend on y and z, but it will depend on x and it will depend on time. Okay, it's still there is a vector. Okay, and I will choose the direction to be along x-axis. Okay, so this is the magnitude, and okay, so I will choose the direction along y-axis. Okay, so this is the electric field directed along y-axis, and it changes with respect to time and x coordinate. It can happen, right? I have chosen this form just for a simplification in calculation, to simplify the calculations. Okay. Similarly, I will choose magnetic field in the following way. I will choose magnetic field in k direction, and I will assume that the magnetic field also depends only on time and x coordinate. It changes with time and x coordinate, but it's directed along z direction. Okay, fine. Okay. So let us draw a picture. So in K frame, okay. So in K frame, okay. So maybe I will, since, okay. So let me change the coordinates. So I will call this as, I will keep this right-handed coordinate system. So it will become x, y, and z. Okay. So this is my K frame. So in K frame, this is the direction of magnetic field. This is the direction of electric field. Okay. And now I have a frame which is K prime. This is my K prime frame. Okay. And its axes are Z prime, Y prime, and X prime. And this frame is moving relative to this frame along X axis with velocity V. So this is the velocity of this frame along X axis. Now the question is how these equations are going to look. This equation, for example, in is going. So how this equation is going to look in K prime frame. So what you need to do? You have to transform all these quantities, this quantity and this quantity. Okay, fine. So let us first see how. Okay, so for this simple, since I have assumed this simplified form of electric field and magnetic field, okay, what will be the curl? I am considering this equation. So curl of B. Okay, what will be the curl? You can say because of this choice, okay, it is simply minus del B by del X. Okay, this B is a function of T and X, and it will be directed along Y. The curl of B will take this simple form. Okay, all these terms, other terms will be zero. You can calculate. Use this form here and see what is curl. Okay, you will get only the this y component non-zero and all other components will be zero. Okay, because of this choice. Okay, similarly, what will be del? There is a del E by del T. Okay, okay. So if you use this form, it will be just del E. Sorry, del E by del T. Okay, it is a function of T and X. Okay, I'm not writing that, and it will be Y cap. Okay, because this direction is along Y cap. Okay, so you have equation. You have now for this choice. Okay, this equation becomes del E by del T. So for this choice, this equation becomes del B by del X equal to minus 1 over C square del E by del T. Okay, so it's the first order equation del B by del X equal to minus 1 over C square, okay, del E by del T. Okay, so this is, I'm still in K frame and we are still in this equation. Okay, I just simplified this equation using this choice. Okay, okay. So now I need to transform this equation using Galilean transformations. Okay. So firstly, we should know how this partial derivative transforms. Okay. How this del t and how this del x should transform under Galilean transformation. And then later on, we will see how this E and B will transform. Okay. So as far as partial derivative is concerned, okay. Okay. So suppose if I consider any function, okay, f of t and x, okay, then del f by del x, okay, you use chain rule, del f by del x will be del f by del x prime and del x prime by uh, del del x prime by del x, okay, plus del f by del t prime, okay, and del t prime by del x, okay. So this is just, so x is a function of x prime and t prime, okay. So I have used chain rule here, okay. So what is del, so what we need, del x prime by del x and we need del t prime by del x, okay. Also we have term like this, we have term like uh, we have this term also, okay, term like this del t, some function and del t. So let us see how that transform, okay. So del f by del t equal to del f by del x prime and del x prime by del t. Remember, there is a t and there is a t prime, okay. You should keep track of prime and unprimes always, and del f by del t prime and del t prime by del t. So these are simple chain rules, okay. So we should know these partial derivatives, okay, but the transformations are given, right? The transformations are given here, okay. So what are the partial derivatives, okay? So x prime equal to x minus vt and t prime equal to t, okay. So del x prime by del x will be 1, okay. Then del t prime by del x is same as del t by del x because t prime equal to t, okay. That will be 0, okay. Then del x prime by del t equal to minus v, okay, and del t prime by del t equal to 1, correct, okay. So this is how your partial derivative will transform. This is any function, okay. So this is how your partial derivative transform. So let us apply here, okay, for this equation. Keep your b and e as it is, just transform these partials, okay. So what we are going to get, okay. So del b by del x in k prime frame will transform. I'm still keeping b as it is, okay. So it will be del b by del x prime and del x prime by del x, but del x prime by del x is 1, plus del b by del t prime by del x, that is 0. So it will be just del b by dx, del x prime, okay. And what will be your e? So de by dt, these will be still functions of t and x, okay. Here this b is still function of t and x, okay. I have just transformed partial derivatives. We don't know yet how this b is transformed, okay. So the story is not complete yet, okay. So del e by del t will be del e by del x prime, okay, and del x prime by del t. Del x prime by del t is v, so it will be minus v del e by del x prime, okay, plus del e by del t prime. del t prime by del t, that is 1. So it will be plus del E by del t prime. Okay, so these will be the incomplete transformations yet. Okay, I have not yet transformed B and E. Okay, okay, but now that I will give as an exercise. Okay, so how to determine this transformation rule of E and B? Okay, how you can determine the transformation of E and transformation of B. Okay, right. What you need to use, go back to your first slide. What principle of Galilean relativity says? The Newton's laws of motion should remain the this m d2x by dt force law must remain same. Okay, now suppose you have a charged particle of charge q and it is moving in electromagnetic field. Okay, so what force does this charge will experience? This F will be equal to what? Okay, it will be q into E plus V cross B, right? So suppose this charge, so I should not write V because V we used for relative velocity. Okay, suppose this charge particle is moving with velocity u. Okay, so it will be u cross B. Okay, fine. Now this force in both the frames must remain same. That is the force law must remain same. Okay, this means that this must be equal to q, and charge, we assume that the charge is also same in that k prime plane. Okay, so this the force law preserve its structure means this is equal to E. Now I will write prime here, and then I will write t prime x prime plus u, okay, prime, so velocity in transformed frame, cross B prime. Okay, yeah,
Sir, how can we assume charges
that is
charge
by
maintains
empirical, that is by
itself?
observation, that is by observation, right? The two inertial frames, you see the same charge, that is by observation.
Sir,
Mhm.
sir, here you have taken velocity u and u prime. Sir, the issue is if a charge is moving, then we are taking this at an instant, right, sir?
Fine,
Okay. Yes.
correct, fine. So this is the instantaneous velocity, whatever that velocity may be. Okay, the force is given by u cross B. It may be changing, but it is just a charged particle in electromagnetic field. Okay, fine. So you can simplify the situation by switching off the electric field. Just consider charged particle in magnetic field. Okay, so you have V cross B. Okay, V could be anything. So whatever that velocity, it will get cross multiplied with B, and it gives you the force. Okay, clear? Okay, it's the detailed information about V is not important. Okay, whatever that V may be. Okay, the force will be perpendicular to u and b, the whatever the instantaneous force. Okay, the point is that
Yes, sir.
this
Yes.
equation structure remains same. So that is your principle of Galilean relativity. Okay, now what will be your u prime? Okay, that means you see u is the velocity of some object in k prime frame. Okay, so suppose you have this frame. Okay, you have this k frame and k prime frame, and some particle is moving in this frame, okay, with say velocity u prime. Sorry, some particle is moving in this frame related to this frame with velocity u. Okay, obviously the observer in this frame will see what? Okay, the velocity of this particle will, x component of this u will be added with v, and y and z component will remain unchanged, correct? So your u prime x component will change by u plus v. Okay, sorry, it will be subtracted because the transformation there is a minus here, so it will be subtracted. It's not added, it will be subtracted. So if you see particle in this frame, if you see velocity vector in this frame to, if you transform that velocity vector in this frame to this frame, then there will be minus plus sign. Okay, but now we are transforming from here to here. Okay, so there will be, so this observer will see this velocity. Okay, ux minus v, because v is along x-axis. Okay, and y and z will remain same. So this is simple composition rule or transformation rule for velocities in Galilean relativity. Okay, so you know there is a one frame, okay, moving with velocity v. Okay, if we have a particle in first frame, okay, with moving with velocity u, how the observer in moving frame measures that velocity, measures the velocity of the particle in k frame. That is the question, and this is the answer. This will be the velocity measured by observer in prime frame. Okay, clear? So obviously, if the particle velocity is say v, okay, and this entire velocity is along x-axis, okay, then obviously this observer will measure 0, because this with respect to this observer, this particle will be at rest. It is as if I am attaching this frame to that particle only. Okay, clear? So now let us apply this here. Okay, so with that, your vector u prime will be in general u minus v, but your v is along x-axis. Okay, so now you use this equation, okay, and find out the transformation rule. Okay, how to find out? I will give the hint. You substitute this here, okay, apply the definitions of E and B field, okay, the directions of E and B field, okay, the way we choose, remember this choice of E and B field, okay, this choice. Okay, obviously since these transformations, this if you see these Galilean transformations, okay, they are not going to change the direction of the velocity any vector. Okay, so this e prime, whatever that e prime vector may be, it will still be along new y cap prime direction, but y cap prime is same as y cap. Okay, so this e prime will still be along y cap direction, and this b prime will still be along z prime direction. So I should write prime here. Okay, what you need to determine is these functional forms in terms of original E and original B. Okay, so this z prime, there is no point in writing prime here because this remains same. So there is only z cap. Okay, so you convince yourself that this E prime vector still going to be along y cap direction, and B prime vector will still going to be along z cap direction. Only this functional form of this coefficient is going to change. Coefficient of this unit vectors is going to change. Now you
Sir,
have
I
to
didn't understand the reason
you
why
see
the
that
direction
Galilean
moved.
you see these transformations. Okay, they are not going to, suppose if there is a vector, okay, they are not going to change its direction because of this, the way these transformations are constructed. Okay, they are not going to change its direction. Okay, it involves
So
only time.
why not?
See it.
Because
See, first of all,
if
they
we
are
consider the
linear.
velocity vector,
Uh,
the direction of velocity vector is changing, right? Because
no,
if we
why
consider,
velocity? No.
Sir,
If it, see, the velocity v, relative velocity v is fixed once and for all. Okay, so this
yes, right.
velocity is this velocity is fixed once and for all. This is not going to change. We are
Yes.
not talking about accelerated frame. Okay, it is just a one frame is moving with constant velocity related to another. Okay, whatever the vector you give me here in this frame, its direction is going to be same. Okay, at least means suppose you consider this x
Sir,
cap unit vector, y cap unit vector, and z cap unit vector. What is going to happen? Okay.
sir,
Okay.
if we consider some velocity vector u bar in the first frame, and it is it has x and y components, and if when we subtract the when we transform it into k bar frame, the x component will be reduced
Which
of the
x component
velocity,
will be reduced? Yes.
and y will not be reduced. So in turn, the direction of the velocity
No. Why
vector,
direction is going to change? See,
because the
see,
x reduced, but
that
y
is the
did
function.
not.
No, but that is the see, one can have this vector, okay, your x and this is y, okay. You can have this u1 x cap plus u2 y cap, okay. These are not going to change. This is what I'm saying. Okay, this may change, obviously. Okay, these things are not going to change. Okay, so what I mean is that if there is x prime will still remain, x prime cap will still remain as x cap, y prime cap will still remain as your y cap. Okay, clear? Now you consider any vector and decompose into x decompose that vector into this frame. Okay, then you apply these transformations. Okay, suppose you consider this vector r vector. Okay, and you apply these transformations. Okay, but one thing you need to be careful. Here we are talking about constant vectors. Okay, there is not, it's not a function of x and x y z. Okay, here we are talking about some constant vector. Okay, here it's not a constant vector, it is function of t prime x prime. Okay, so you have a vector in tx coordinate that you are calling as e. Okay, and you have another vector which you are calling as e prime in t prime x prime frame. Okay, these vectors is not going to change the direction. Okay, so why? Because if they change the direction, okay, your force law will not remain same. Force law will change completely. Okay, in one frame, then you will have the situation in which in one frame, suppose ex is 0. Okay, suppose in this frame the x component of electric field is 0. Okay, then you will, then some observer here will measure the its displacement along x-axis. He will count something. Okay, in this frame, okay, if ex component is not 0 of that new electric field, okay, then this observer will measure something which is different than this. Okay, is it clear or not? This
Yes, sir.
rule should not, this force law should not break. Okay, in that case I will be have, I can create a force in some direction if the rules, if the force, if the vectors do not match, if the direction of the vector do not match, then I can create a force which was not there in this frame. I can
Yes,
create
sir.
extra piece which
So
was not there.
that will happen in non-inertial frames where
That might
we
happen in non-inertial, it depends
yeah,
on your
so
transformation.
we introduce a pseudo force, for example, right?
Correct.
So
Okay, but that is completely different. Okay,
right,
so
right.
here as far as this velocity is concerned, these transformations are in they are constructed in such a way that this your vector, if there is a rule in assigning the vector, okay, then the vector should transform with direction in same way. If there is a rule, and if you are imposing that that rule should not break, like for example here the Newton's equation of motion imposes a rule, and you are saying that Newton's laws of motion is one rule, and you are saying that that rule we should not break. Okay, so then you are not allowed to change the direction. Okay, so
So
now
double derivative vectors will not change their direction, but single derivative can.
single derivative, but
Right.
in all, so yeah, so here there is only one, right? There is only in A there is only E and B is coming. So if I in one frame if Ex is 0, then another frame Fx should be 0. That is what it says.
Yes, sir.
Okay, fine. So now your job is to find these new functions E prime and B prime in terms of this E and B. Okay, remember these will be Tx and this will be Tx. So you need to determine this E prime B prime in terms of E and B. Okay, you substitute this here. Okay, in place of this you substitute this. Okay, then you simplify a little bit, break into component wise, and you simplify a little bit. You will get the following. What you will get is E equal to E prime plus V, E prime plus V times B prime, but B and B equal to B prime. This is what you are going to get. Okay. So remember, when I write E prime, there is the arguments will be T prime X prime, and when I write B prime, arguments will be T prime X prime here. When I write E here, then arguments will be Tx. So B remains same, but E is going to change the functional form. Okay. So now you use this equation, use these transformations here. Okay. So here you need to replace this E, but see what you want to write everything in terms of prime quantities. Okay, so we managed to write the partial derivatives in terms of primes. Okay, prime coordinates. Okay, now we need to write E and B here in terms of prime coordinates, prime variables. Okay, that is E prime and B prime. Okay, so use these equations here, here, and here, and see what you get. You will see that this, what was our starting equation? This was our starting equation, right? You will see that this equation will not preserve its form. Okay, you will generate some terms which are higher derivatives in uh, so okay, so for example you will generate the terms like this. Okay, so you'll generate velocity dependent terms, something like this. Okay, or v square del E by del T, something like this you will generate, you are going to generate. Okay, sorry, v square del B by del X. These kind of terms you are, apart from your original term. Okay, del B by, so it will be del B by del T prime will be equal to del E by del T, and then there will be 1 over C square. This will be there, plus there will be some terms, extra terms, which will go to 0 when V equal to 0. But if there is a non-zero V, these terms will be there. So the rule is completely different. Hence here, this equation del cross B equal to minus 1 over minus or plus, it will be minus 1 over C square del E by del T does not preserve its form under Galilean transformation. Okay, so you do this exercise. Okay, Okay, so from this, okay, you find out the transformation rule for E and B. Okay, and using this, you show that uh, this equation, the Maxwell equation, okay, does not preserve its form. Okay, and you can do for that other Maxwell equation also, del cross E equation, and you will see what you get. Okay, but there is a simpler way to see this. Okay, so these are you used Maxwell equations, but there is a simpler way to see this. Okay, what is that way? Suppose you have a source of electromagnetic waves, okay, and it emits the suppose spherical wavefronts in all directions. Okay, it emits spherical wavefront in radially outward direction. Okay, so at given instant of time, okay, what will be the equation of this spherical wavefront? Okay, in 3 dimension it will be x square plus y square plus z square equal to, suppose the speed of this electromagnetic wave is c. Okay, then the distance covered in time t will be ct, that will be the radius of that spherical wavefront, and it will be c square t square, right? So this will be the equation of spherical wavefront at time t. Okay, yeah. Now this spherical wavefront, okay, is nothing but the solution of Maxwell equation in vacuum. Apart from the source, okay, it is entirely free space. Okay, so this spherical wavefront is a solution of your Maxwell equation. Okay, these are basically spherical waves. Okay, and this will be a solution to Maxwell equation. Correct? Okay, so now suppose if I consider an observer which is moving with velocity v, say along x-axis. Okay, fine. What is going to happen? What kind of wavefront, what kind of wave it will see, this observer will see? Okay, then what you need to do? You need to transform this equation, right? What are the, according to this Galilean transformations? Okay, then you will see that this will become x prime plus vt prime whole square, okay, plus y prime square, y remains same, so y prime equal to y plus z prime square equal to c square t prime square. Okay, t becomes t prime. Obviously this is not an equation of sphere, equation of spherical wavefront. That means the solution of Maxwell equation is different now, right? What was the spherical wavefront in one frame, it is not no longer a spherical wavefront in another frame. Correct? Fine. So you need different equation whose solution is this wavefront. And that equation will be different than Maxwell equation. Is it clear? Okay. So your in all, your Maxwell equation or your electrodynamics does not respect Galilean relativity, principle of Galilean relativity. I used here one hidden fact. I assume that this C remain constant. Okay, but that is from observation. From observation I see that C remains constant, and if I apply the Galilean transformations, then your this spherical wavefront does not remain spherical in other frame. Okay, clear? Right? So Maxwell equations does not respect Galilean relativity. principle of Galilean relativity. Okay, but we do observe the same velocity of light in all frames. Okay, so that means something need to be added in this principle. Okay, from observation we know that the velocity of light is same in all inertial frames. That is your Michelson model. I hope you have done that already. Okay, so from the experimental side we know that this velocity of light remains same in all inertial frames. Okay, so now suppose if I say that I add, suppose if I have one rule which is laws of motion remain unchanged in all inertial frames, and second, the speed of light is same in all inertial frames. Okay, these constitutes, these two, 1 and 2, constitutes the principle, or you can say postulates, whatever the principle. Okay, so let me, we don't have to use all these jargons. Okay, these two statements constitutes your spatial theory of relativity. Just okay, so remember this was there already. Okay, the extra point is this. Okay, and now because of this
ऐकू येतंय का कोणाला? हॅलो
हॅलो हॅलो सर हॅलो
त्यांच्याच सरांचा प्रॉब्लेम झाला होता काहीतरी गेल्या दिवसाला.
हा काय झालं?
Sir has messaged. Okay. Internet is down. Chalo, bye bye.
Okay, then let us end the meeting.
Yeah, okay. Bye bye.